Hello, good morning. This is Professor Khan, and this week we will discuss how do we connect series and parallel circuits and how would the load affect the voltage, amperage, and resistance. And this is Energy System Lab 1 and week 5. And as you can see, we're going back and forth between doing mechanical work and some electrical work as well. Okay, let's start. So the theoretical learning objectives is how can we tell a series circuit from a parallel circuit as we go along, and how would we connect that in order to connect those loads in series and parallel, and we can take measurement to see how would the voltage is different than the amperage than the resistance for both cases. So the hands-on experience will connect three loads in series and measure voltage, amperage, and resistance. We record the findings and see if it agrees with whatever we have on paper, and also do the same thing for parallel and see what would the difference be between those two. So a series circuit are connected for safety. They consume more power because, again, we said that resistance does add up. There is only one path for the connection. So hold on, let me go back here. So we have loads into a circuit. This is my voltage, and they are in series, so we know that resistance will add up. So it's connected for safety. It consumes more power because resistance is higher, and if we look at Ohm's law, as the resistance gets higher, the voltage will get lower. And there's only one path, so if we cut one of those paths, nothing will work. So we'll verify that by taking one of the light bulbs and see if it's going to work or not. And it's very simple to connect. We only connect through the hotline. This is what it looks like, and these are switches here. They are connected in series for safety. If one of those switches goes out, the whole system will go down. So resistance and current, the current draw is the same through the entire circuit. So we'll go with the clip-on meter between the light bulbs that we will connect and measure the current, and you'll see it's the same. The resistance will be higher, so we'll measure the resistance from beginning to end and see what is the total, and measure the resistance for each one of those light bulbs as well. Voltage. So voltage is completely used, so you will notice when we do voltage using the probes and the multimeter that the voltage in the beginning at the source is 120, and for the first light bulb will get 120, the second one will get less, third one will get less, until the end of the circuit where we have 0. So I will add them up to verify that information. For parallel circuit, there is more than one path, so the resistance will go into 3 paths. And as you can see, there's redundancy, so if one of them goes out, we still path for the circuit, and the other two will still work. It will lower the load in the circuit because we said resistance will drop. The total resistance will drop, and it will be lower than the lowest resistance in the circuit. This is an example of 3 loads connected in parallel, and the total resistance will be lower than all those 3, and any of those go out, the other 3 will still work. The current will be divided, so the current will be drawn based on the load itself, and for each little resistance the voltage will be the same, but the resistance will be different, and the amperage will be based on the resistance. So the amperage for each one of those circuits will be voltage over resistance. So depending on the resistance that we have, this is the amperage draw, and the total amperage will be the addition of all those 3 or whatever branches you have for resistance for loads added together. And this is the formula of how do we add resistances in parallel, and we'll do that in paper. Then we'll go and verify that on the board. Voltage will always be the same. Every load will get the same voltage as the other. Again, the analogy between resistance and water circuit. If we have a pump similar to our source, the flow is the current, and the smaller the resistance, the smaller the current or the flow going through it, and the same thing goes for electrical circuit. So this is the board and we will connect the switches as we did before, and this time we'll connect 3 light bulbs in series, take measurement, then we'll do them in parallel and take measurement. So we will need to use the multimeter. So since we're using light bulbs, it's really difficult to measure the resistance of a light bulb once it's off, because the temperature does change the resistance. So we said whenever we run amperage through any load, 2 things will change. It will start to heat up and it will generate magnetic force or range. So the best way to measure the resistance is to measure the voltage and divide that by the power. So if we look at these powers, every light bulb has a power. So the ones we are using are around like 7.5 watts. So we have the power, and the voltage is measured by 120. So 120 square divided by 7.5 will give you the resistance for that light bulb. Again, it will vary a little bit based on the temperature, but this is kind of the average light bulb current draw. And that will help us estimate what is the current that will be drawn from that light bulb. And we did that also in lab 1 when we measured the amperage and we tried to see if it's reasonable or not. Okay, here is the calculation based on the 4 components, and you can see all the variation possible, but all you need is to know is Ohm's law and power law, and this is the combination between them two. Okay, let me do something else here. So we will measure the let me do that. This card, I'll put another slide here. So if we have the circuit in parallel, or let's start with the series one. Thinking about the resistance. Resistance. So if we connect those 3 light bulbs in series, the resistance for each one of them will be 120 square over the watt withdraw or the rating which you will find written on the light bulb. So if it's 7.5, that's what we have for the small light bulbs. This will be 120 square over 7.5. So we have 1920 ohm. That's for each light bulb. So in series, that will be 120 plus 1920 plus 1920. That will give me 5760 ohm. So the voltage, the amperage draw expected will be 120 over 5760, which equals 0.02 amps. That is when we do things in series. So we're gonna do this calculation beforehand, then we'll go and verify that we're getting the same amperage. So let me erase this and do the same thing for parallel. So we said the resistance for each one of those light bulbs, the small ones that we're going to use, is 1920, and we're going to connect them in parallel. So R1 over R total will equal 1 over 1920 plus 1 over 1920 plus 1 over 1920 as well. So if we do the math, since we have the same light bulb and the same numbers, it will be easier to do. So it will be 3 over 1920 again, because we have the same common denominator. 1 over RT, so 3 over 1920, and I get, after I do the flip, RT will equal 640. Okay, and by doing so, the amperage will be 120 over 640, and that's equal point, I'm gonna put it over here, it's 0.1875. That will be our amperage based on the voltage. So hopefully this makes sense a little bit, and we'll verify these numbers. Please write them down before we go to the lab, and we can show you this video as well during the lab so you can know what number to look for. And since this is very small, it will be good to wrap the wire in 2 or 3 loops that take the measurement and try to see if we get the same or close number to that. Okay, I will see you in the lab, and thank you for your attention.